Okay, I believe we are at lecture 10. All right, we'll move on to the second part of the infinite square well particle. All right, so we'll cover the second LO with regards to this. All right, so if you remember the infinite square well potential particle, right, must exist within 0 and L, and these are the possible waveforms for n equal 1, 2, 3. These are called quantum states. Right, so sorry, quantum number. Right, so is it only can be n equal 3? No, it's just like your harmonics in your standing wave under superposition, right? Of course, you can go 4, 5, 6, 7, 8, 9, 10, all right? But we actually want to know what is the energy associated with each of these quantum numbers, right? So the energy associated is given by this. Again, I remind you, this formula is given in your formula sheet. You do not have to memorize. I'll just give you a derivation, okay? Energy K of a particle is given by half mv square equal to momentum square over 2m, right? This one I derived for you before, so I'm not going to do it again. And from De Broglie relationship, which is momentum equal h over lambda, I can substitute this into the p square over here. All right, so when I substitute into p square over here, it become, the top become h square over lambda square. So the lambda you just bring down, then you get this one, right? And if you observe how lambda varies with n from the diagram, you'll observe the relationship between lambda and n to be lambda equal 2 over nl, right? Because in this case, right, lambda is 2l. You see that? So if n equal 1, right, lambda 1 equal 2 divided by 1l. Then isn't that lambda equal to L? Right, you can try that for n equal to n equal 3, okay? This is the relationship between lambda and n and L, right? You can derive from drawing this graph. So I wouldn't memorize this lah, right? And therefore, if I substitute this into this thing over here, I'll get this equation, right? So lambda square is this lambda that I'll substitute inside. So 2 square will become 4, right? So the denominator has a 4 inside, multiply by 2, that's how you get 8. Then you divide by n square, so that means go back to the top. That's how the n square goes to the top here. Alright, so it is En equal n square h square 8 ml square. Right, n equal 1, 2, and 3 lah. Obviously 4, 5, 6, 7 also can. Alright, so to understand this further, you can play with this website. Alright, I think you can Google St. Andrews ACUK lah, or you can just type this out in your browser. Okay, I'll show you how to play with this website. Right, so this is the actual website. Alright, sorry. Try to resize it for the window again. Okay. Apologies. Okay. Yep. Alright. So yeah. So what's cool about this is that you can actually see everything here. Right. This is the probability density graph function, which is psi modulo square. So you get this one. Right. Clearly, you know how to use this now. I've been discussing this a lot lah. So I'm not going to talk about this. Okay. Classical probability density. What does this mean? This means that, right, for particle in finite square well, it must exist between 0 and L. Classically, the probability of, if it was a classical case, the probability of finding a particle is equal everywhere. So that's why the red line is here. Right? But you should know that for a quantum particle, right, it follows the wave function. Right? So the wave function square, modular square of the wave function give you this one. So the particle in this case, this for n equal 1, right, quantum number 1, for this case, the particle is most likely found in the middle because the probability density function has the greatest area in this volume here, right? And of course, the probability gets less as it extends towards the L value. Of course, this is the same if, this is not the same if I change the energy state to 2, right? Now, the electron is unlikely to be found in the center. All right, let's assume it's electron. It's likely to be found here or here. All right, and so on and so forth. There's 3, 4, 5, 6, as many as you want. Okay, can? All right. So anyway, what we'll do, you can play with this yourself, clearly. But what we'll do is we'll try the challenges. So we'll see whether you understand the topic well or not. Right, consider a box of finite width. That means like what we talked about, infinite square well box. Right. Choose one or more correct answers. The larger the quantum number n, right? So as n increase, what happens? Does the wavelength become bigger? All right. So you can check right? So this is the wave. This is half the wavelength, right? Because wavelength is supposed to be like that, right? So if the quantum number become bigger, you should be able to draw this yourself, but I'm showing you the app because it's easier, right? As the quantum number become bigger, the wavelength become smaller, right? You can see that, right? It's just visually observable here because this L is the same. Greater the particle's total energy, right? This one we have to go back to the formula we discussed earlier, which is this one, right? So if you look at this formula here, the greater the number of, the greater the quantum number, is it energy become higher? Answer is yes, right? Because it varies with, the energy is proportional to n squared, right? So clearly this one is correct, right? Number one is wrong, number two is correct. Greater the amplitude of wave function x, right? So does the amplitude get bigger? Remember how to find amplitude, you must do normalization, right? So in front, we talked about normalization before, which is this part, right? This area under graph thingy, right? I must find that the area under graph of wave function modulus square equal 1. That's how I find A, right? If you look at how I find for this one, you realize that I found the amplitude of this wave function to be square root 2 over L. If you go and try for this one and this one, which you should try, please go and try, okay? I know a lot of times I tell you the answer is like that, then you all don't bother to try, but it's really important that you all go and try and error yourself and get the answer correct, all right? So anyway, I'll just try and adjust this properly. Okay, yeah, all right? So you'll find that the amplitude for this and this is all the same, all right? You have to try, okay? Please go and try yourself, but I'll just show you in the graph. Okay, the amplitude, can you see? No matter what I press, the amplitude is the same. Square root 2 over L, not, right? So the amplitude is not affected by the quantum number, right? Because I'm changing the quantum number, right? So this one is not changed. Smaller the wavelength, is that true? Answer is yes, because just now we already say not this one, so must be this one. It's observable again, right? And see wavelength becomes smaller, right? The green graph, right? So submit. Hope it's correct. Yeah, okay, lucky it's correct. Right, let's move on. Consider a particle with quantum number n equal 9. Alright, so nice they pick for you already. Choose one or more. The greater the width of the box. That means if L become bigger, the smaller the particle's total energy, right? Particle's total energy, does it depend on L? Right? We have to look at this formula over here that we just learned, right? Yeah, it does, right? So as L become bigger, what happens to the particle's energy? It actually drops, okay? Right, because L is in the denominator. So smaller the particles total, yeah, this one should be correct. Right, so greater the particles total energy. Correct or wrong? Okay, you try and think yourself. I think maybe I should pause and let you try yourself. All right, maybe you pause the video and try yourself. Okay, we're back from the pause, right? Sorry, I think I should have really given you time to try and do it yourself. Right, anyway, the greater the particles total energy, clearly wrong because this is correct, then this must be wrong, right? They're opposites, right? Smaller the wave function, smaller the wavelength, right? N equal 9, right? So if n equal 9 is fixed, does the wavelength change if L increases, right? Uh, right, so if L increases, what happens, right? The number of waveforms here will be the same, all right? Because the quantum number decides the number of waveforms, right? You can think of this as related to the harmonics in your superposition, right? So does the wavelength become bigger or smaller, right? You should expect that if L get bigger, it will stretch the wave. So the wavelength get bigger, not smaller, right? And then what happens to the amplitude, right? Amplitude, if you think about it, is always derived from the probability density function, right? That means actually I'm trying to calculate this square to be equal to 1, right? So if L is dragged out like that, L become bigger, right? Then this part should drop, which means amplitude should drop, not greater. So I think this one only 1 is correct. Yeah, okay, great. Alright, so only 1 is correct. Okay, Ken? Alright, let's move on to question 3. Can you please try this yourself? Okay, pause and try yourself. Okay, we're back from the pause, right? Consider a box with fixed width, right? So, I think it's this box, yeah. For the state shown, find the probability of finding the particle in the shaded region. So, what's the probability of finding the function, particle in this shaded region, right? You just count the area on the graph, lah. So, it's 1 of this area, 2 of this area, 3 of this area. So, 3 of this area sum to 1. What's 1.5? 50%. Right, should be quite easy. Yeah, okay. No problem with that. Okay, move on. Consider a box with fixed width and the state shown, shade region less than the total width of the box. for the quantum probability of finding the particle in this region identical to classical probability of finding the particle in this region, and press submit. Right. So classical probability of finding a particle in a region between 0 and L should be equal throughout. So this red line is the probability of finding the particle in this region. All right, that means this classical lah. All right, so the classical is like uh is equal probability throughout. All right, so what is the set out a region where the quantum probability of finding a particle in this region is identical to the particle. Yeah, so it's 50%. Right, so it's 50%, and we should find something like that. Right, I think something like that. Yeah. Can so this 50%, right? So the classic particle is equally likely to be found anywhere inside the box, right? Okay, move on to the last question. For fixed width, how does the quantum number, how does the wavelength lambda depend on the quantum number n? I think we found the relationship already lah, but we can sort of derive it, right? Right. So how does wavelength relate to quantum number? So this E10. I think it doesn't matter what E you find lah. You get the relationship, right? So I just find one with a nice lambda. So yeah, so this is 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength, 5 wavelength. So 5 wavelength equal L. So lambda is equal L over 5, right? But this is the energy state 10, right? So how to get the n inside the term, right? So I must place n somewhere that this is 5 wavelength equal L. So 5 lambda equal L for energy level 10. How to fit the n such that I get 5 lambda equal L? Let me think. Yeah, actually, you should pause and think as well. Okay, so the answer should be somehow I sub n into the equation, right? The answer should become 5 lambda equal L lah. So 5 lambda equal L, lambda is L over 5, right? So if I substitute 10 into the n, I should get lambda is L over 5. So where do I substitute 10 to get lambda is L over 5? Right, this one, right? You see this? Right, I substitute 10 in the n, then I get lambda is L over 5 because 2 over 10 equal 1 over 5. And so I think it should be this one. Yeah. Okay, Ken. So I think with that, we have some sensing of how to do one-dimensional particle in a box style questions. All right, I think with that, I'll end this lesson. All right, see you in the next one. I think we have 2 more.